In this work, we developed a model-based approach to enable accurate MR parameter mapping from highly undersampled data. As we know, MR parameter mapping, like T1 mapping or T2 mapping, provides important quantitative information for tissue characterization. But to obtain accurate parameter maps, the conventional approach acquires a relatively large number of images with different contrast weightings. This often leads to long acquisition times, especially for applications requiring high spatial resolution or broad volumetric coverage. Here we present a novel model-based reconstruction method integrating the Lorentz constraint and sparse constraint for accelerated MR parameter mapping. As we know, both Lorentz constraint and sparse constraint are mathematical models that can be utilized to enable signal recovery from sub-Nyquist measurements. In this work, we propose a unified mathematical formulation to nicely integrate the two constraints, and we demonstrate that the proposed method can lead to significantly improved performance than using a single constraint. For MR parameter mapping, here we use the Lorentz constraint to capture the correlation of relaxation signals associated with different tissues. Complementary to the Lorentz constraint, we use the structure sparse constraint to model the spatially shared edge structure. Additionally, we design a specialized data acquisition scheme to pre-estimate the temporal subspace for the image model. This not only simplifies the computational problem, but also improves the reconstruction performance. On the right-hand side of the slide, we show representative result of applying the proposed method to a T2 mapping application S3T. We perform reconstructions using the proposed method as two acceleration factors. One is at 4.1 and the other is at 8. To demonstrate the benefit of imposing the joint constraint, we also show the reconstruction results using a single Lorentz or structure sparse constraint. As can be seen, as a moderate acceleration factor, all three methods perform fairly well, although the proposed method has better performance than the other two. But when the acceleration factor was increased to 8, the performance of both Lorentz reconstruction and structure sparse reconstruction significantly decreased. Qualitatively, we can see the edge structure of the T2 map obtained from the structure sparse reconstruction are severely smoothed out. For the T2 map obtained by the Lorentz reconstruction, we can see the severe artifact induced by the U conditioning issue. Quantitatively, the T2 values from the two methods also become less accurate. In contrast, by simultaneously enforcing Lorentz and sparse constraint, the proposed method has better preserved edge structure and reduced artifact. It also leads to much more accurate T2 values.